Oi, today's paper is adversarial training using feedback loops. This one's pretty interesting. I'm not actually very aware or into at all adversarial training examples or anything, but they are types of attacks on models. This paper attempts to solve them by introducing control theory, and I think the kind of feedback loopiness of this model, is really cool, and I don't quite have it there yet, but I'm feeling some inspiration coming on from this paper in terms of architectures that could be happening. It's also related to my recent video on neural networks self-modeling themselves that I think might be interesting. Please let me know what you think of it. I think there's something there to combining those two approaches. I will talk more about that second video towards the end of this video, but check it out. And also, it's by Virginia Tech. Some Virginia Tech, I think, grad students at the time, not quite sure, but GOKIES. So yeah, let's get started. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my link tree. Let's get started. So, a bit of preliminary knowledge. I do not believe we have discussed this on my channel before, but there is a phenomenon called an adversarial example, where basically a very small change in the input, the actual initial vector in the model, could lead to large changes in the output. Now, an adversarial attack, its whole purpose is to find these inputs which lead to large changes in the output, right? Again, I'm not very into that whole subfield, but the idea being that there are vulnerabilities inherent to these models due to the way that gradient descent just naturally trains them, such that if you actually have access to specifically editing the initial input vectors to some transformer or something, you could test out a bunch of tiny changes that potentially ruin the model's output. And by ruin, I mean, well, imagine getting around the bounds of RLHF alignment and getting the model to say something that is terrible or unsafe, right? Now, the goal to make robust neural networks is to make networks that are robust to adversarial inputs, meaning that there are no easy to find, obvious, very tiny changes to the initial input that would result in large changes to the final output that could potentially be unsafe or break so whatever structure the model is part of. Now, how do we usually find these small changes? It's pretty simple. We just look at gradient descent, right? I'm not super clear on this and how it's actually done, but you take either the input you already have or the desired output, not quite sure the deal there, and you look at your actual input and you just check the gradient and move in steps of the gradient that lead you away from the regular output towards some other output. Now, the training procedure that works against this and tries to prevent this from even being possible is referred to as adversarial training. And it actually uses these maliciously edited, perturbed inputs paired with the correct outputs to enrich the training set. Meaning, during training, you actually use these small changes, these adversarial examples, and you tell the model, hey, don't be fooled by these small changes. The correct output is still X, Y, or Z, right? With the idea being that during training, you can robustify your neural network against these attacks. Now, background on a separate field, negative feedback control. This is a very general mechanism by which the outputs of a system are stabilized in the presence of unknown perturbations. Control in general, I'm only vaguely aware a little bit, but the idea is you have some systems, such as, for example, these reverse upside down pendulums trying to get something to balance, or one that I'm more familiar with that was more in the older days of pre-deep learning AI for self-driving was trying to get a car to stay in the lines of the actual lane. In these systems, whenever the actual object would veer off course from the desired output, you learn a model that is designed to learn how much to steer it in a certain direction or whatever it is, how much to provide negative feedback to put the desired thing back in its place. So, for example, with those upside down pendulums, when you have like a balancing, say, pencil or something, right? If it starts to fall over, your model learns your model learns the amount of push it needs to provide to get it to balance again. Or conversely, for the car example, when the car starts to veer out of the lane, the model would learn how much to turn the wheels to get it back in lane. Specifically, in a feedback control system, the controller monitors the values of output variables and compares them with reference values. Output variables being the car's position relative to the actual lane, reference values being the ideal position in the middle of the lane. The difference between the actual and desired values is fed back and used to generate a control action, aka the turning of the steering wheel back into the lane, that nudges the system output back toward the reference values. Now, the idea of this paper is to look at how can we use negative feedback control to combat adversarial examples and create better adversarial training. So they create a new architecture named feedback neural networks that incorporates this feedback control. So consider some input X as the reference, our actual baseline, right? Like our correct in the center of the driving lane, and the corresponding reference neural network output Y, right? It's the actual correct answer of the system. Then consider a perturbed input, a actual small change in the input, X plus delta X, which is passed through the primary neural network model to obtain a predicted output. And of course, since you edited that input, now your output as well will be different from its initial value, right? You then take this predicted output that has a difference now that is potentially adversarially messed with, and then pass it into the controller neural network model. So a separate neural net model, which produces the feedback perturbation delta x prime. So this new controller model is itself a function of the perturbed output, the actual wrong, edited, perturbed, messed with output of the main model, and then its own parameters. And it outputs a proposed perturbation to the inputs, a proposed perturbation that is meant to counteract the original perturbation. So x or delta x prime counteracts delta x, at least in theory if the model's trained well. Now, this new corrected input, which we'll call x squiggly, I guess, is not just the initial correct, reasonable, regular input that you would use training any other network. It's also the adversarial perturbation and the controller network's attempted fix adjustment perturbation, with the idea being that when propagated through the actual primary neural network, this should approximately recover the reference output, y. Meaning, when you feed these three through the system, the original inputs, the perturbed mess with hack, and then the attempted controller's fix adjustment, it should hopefully output something close to the original desired output that you would have gotten if you had only inputted the regular, reasonable, not been messed with input. Now let's take a look at an actual diagram of this to help display what's happening, right? As we said earlier, we have our initial input that is then perturbed, the delta x. When you feed that through the model, we're going through the dash line, follow the dash line. The actual primary model outputs for us what would be the desired output plus the effect of the perturbation, delta y. That gets fed in to the separate neural network, the controller network, which is trained to output a delta x prime, such that now we're on the dark line, right? The not dash line, such that when you add on our delta x prime and you feed that back again through the regular neural network model, you do in fact get the desired regular output y, as if there had been no perturbation. Now you may notice, in theory, we could actually do this multiple times if our desired output y was not quite perfect and it was still off, if the controller network was not doing well enough. You could do it multiple times. You could even parameterize, like define the controller network itself as a recurrent neural network, as if it was its job from the get-go was to do this multiple times and keep editing until it finds the perfect level of delta x prime. However, during their own experiments, they observed that passing information through the controller network multiple times did not significantly improve the robustness accuracy. Now, that may change for more complex networks or different data distributions, whatever it might be. I'm guessing the way that you would think of it changing is if the controller network is much smaller than the actual primary network, that would probably be increased odds that you would want to pipe it through multiple times. Whereas if the controller network, which I believe happened here, is the same-ish size as the regular main model, then it's probably well big enough to do the actual fix all in one go. It might be the case that it's never useful to do that, though. We don't actually know. I don't believe they found any case where it was, but again, they didn't test all scenarios. I think in a scenario the controller network is much, much smaller than the primary one, that might be the scenario where you actually find this useful, or just certain data sets that might have some kind of intrinsic uh, recurrence to their structure might find it helpful as well. Now we can go take a look at the actual algorithm itself. First part, pretty simple, is just regular training, sample your batches with your input and your output ground truth, right? And then go ahead and update the parameters of the regular model as you would gradient descent, atom, whatever. Where it gets different, first up is a for loop that iterates over the number of adversarial attack steps, k. Now, we said a second ago, of course, only one attack step, or only one, the network only needed one adjustment step to actually work. So I believe that also means you can just train on one attack step. I'm a bit unclear on that. If you think you know, let me know down below. But I'm pretty sure this for loop can be just a single operation unless you actually are going against what they just said and choosing to do the recurrent style of this. But so for me anyways, I'm gonna assume it's just one time. And then what you do is you take your primary model, you input in and find its actual loss value currently, take that gradient rate, so you're just finding the gradient of the loss function as you already really had over here. And you don't even need the full actual gradient, you just need, well, let me back up a little bit. You then, if you are doing the for loop and actually doing the full for loop with many iterations, you would add that to whatever your previous iteration found in the for loop was. But if you're not doing a for loop, just doing one step, I believe you can just ignore that part. Then you take that value and you can actually ignore the magnitude and whatnot of the gradient. You're just looking for the sign, positive or negative, and you multiply those ones and negative ones by the actual step size of your perturbation. However, again, that is a part of the for loop. That is just if you are splitting up your perturbation into many different steps. If we are doing just one, I believe then this can just be ignored as well. But then the actual interesting part-ish, I guess, is epsilon, right? Which is your magnitude of maximum allowed perturbation. So you have to assume here how large a perturbation will be, and then this model setting training will only work, I believe, up to the actual maximum size that you train for. Again, I am not big on the adversarial example field. I don't know how big of an issue that is. Is there an actual realistic limit as to how large a perturbation would be? I believe at some point. I just don't know how to tune that hyperparameter. Not my thing. But I guess you have to choose that is when you're thinking about someone adversarially attacking you, I guess, how large of a perturbation do you expect them to actually use? I imagine perturbation's too large, it just ends up in an entirely different part of the representation space, and who cares anymore, I would guess, but I'm not quite sure how that works. And that gets you your actual perturbed final input, and then you take that perturbed input, the x plus delta x, right? You take its input through the model, run it forward, right? And then take its loss with respect to the actual correct value you initially used. So the same initial everyone always uses update mechanism for stochastic descent, atom, whatever. You instead of inputting your regular input, you input your new perturbed input, take that loss, that gradient, and you update your parameters accordingly. So if we go ahead and look at results, it's actual accuracy results under different attacks. So each one of these is a different attack. The first one, nat, is actually no attack. And then on the vertical column here, we have different methods, with flat being ours, I believe. And they trained a ResNet 18 on CFAR 10. And those are different other models, other methods of adversarial training that do not use control networks. They use something else. I have no clue how they work. But looking at accuracy under these different attacks, we see a bunch of bold lines down here, right? All but one of the scenarios. This method did the best, it seems. That one scenario did not do the best, was under no attack at all, meaning that whatever method this is, it's called FAT, seems to have very little effect on the actual base model and performs very well. The rest of these look to be roughly in line with each other. And actually, even though this one method has first place under no attack, our method here has second and third place, the two versions of it, it seems. I'm not sure what this second version is, though. Feet, I'm not quite, I cannot tell what that is or why it's different from the regular one. Same thing under a different model, similar, even better results. This one actually does perform best under the no attack scheme. and then we do ResNet 18 again, train on CFAR 100. These ones do not do as well. It's curious, it does succeed in one of the attacks, and it seems that a different model, a different method, sorry, seats actually performs best in the rest of them. But that seat method, for some reason, it just doesn't have any mention of anything on the one attack that we've done best on here. Meaning, I'm guessing it actually either two things happened. Either they weren't replicating, they were just grabbing numbers from other studies and like copying and pasting them in, and those studies happened. This study happened to have not tested against this attack, or there's something about this method, something about it that actually prevents it from even being used on this attack. It is completely not applicable. Not sure which of those are the case. So for some reason, when we go to CFAR 100, we are no longer performing number one best. However, when you look, I'm just eyeballing it real quick. From eyeballing, it does seem like this method is actually a close second or third across all those attacks that it actually lost out to first place in. Before we get to my general thoughts, one last little thing from them is that in their future work, which I believe probably already happened at this point, this paper is August 2023, so I guess it may not have happened yet, but there's almost a year. We're at what, 11 months from then. I'm guessing there are papers that have come out since then. But they said in their future work they wanted to study the use of features from other layers of the original neural network to improve the resulting robustness of the feedback neural network. So it sounds like instead of just using the input and then training on the output, they want to actually allow the controller model to look at not just the input of the main model, but also at the features and maybe the weights or whatever, but the features of the main model across all of its residual connections, or some of them, and use that information to help improve the controller network. I think is a good idea. As for my thoughts, the connection I made with this paper that got me curious about it was from a recent video called Neural Networks Modeling Their Own Weights. I will try and put the link in the description and also have it as that final video that pops up on the screen at the end. And in that video, they asked some intermediate layer of the model, which is regular feed forward neural network, I believe, to regression loss. They added a linear layer onto it separately, separate branching, just one linear layer that goes off into a different direction. And they train that linear layer to regress upon, I believe it was the final output, but the intermodal connection and whatnot seemed interesting to me. It seems like there's a connection here that could be made in building an architecture. I like this idea in general of not just residual connections, but kind of more intricate ways of layering and connecting throughout a model and in reverse directions and things. So I don't have any actual solid anything to say about this. Just my intuition says that there is something interesting to be done here with combining that previous video of mine, like that paper, with this paper. But that's all I really got for you today. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.